Okay, so we have a couple of random variables that are being combined because we have two stages of a manufacturing process. And the first one has a mean of 28 and a variance of 5. All right, now the time required, so anyways, the next one is mean of 17 and a variance of 4. So the key thing right here is that we're talking about a variance. Okay, so we already know this is, so if I call the first one x, the mean of x is 28, and the variance of x is 5. All right, mean of y is 17, and the variance of y, actually, I'm reading this one correctly this time, though. If I get it wrong, you can tell me what I didn't read correctly. So now we got 4. So to get the combined, since we're combining both these, to get the combined time, the mean is going to be just these added up. That's 45. The standard deviation, because that's actually what we're concerned with, for x plus y is going to be the square root of the variances, which is just 5 plus 4, which is 9. So the square root of all that is 3. So there's our standard deviation. So now we need to figure out 50 is the point that we're interested in. So we need to find the z-score. What we've just created here is a new normal model that has a mean of 45 minutes, standard deviation of 3 minutes. So that's going to be, sorry, I should put 48 right here. This is 42. And that means 51 is over here. So 50 is right about here. And we want to figure out the odds of getting that time or higher, not the odd, well, yeah, the probability of that. So it's going to be x minus mu divided by standard deviation for our z-score. That's going to be 50 minus 45 divided by 3, and that gets us a z-score of 1.67. So we want to just get the value, the normal CDF calculation going from 1.67 z-score up through, we can just put 99. So if we do a normal CDF calculation on this from 1.66, repeating, you can put that where you want, we get 0.0478. All right, and that is answer A. So the most popular answer today was the correct one. If you got this answer, it's incorrect, but you had the right idea. This is if you didn't read this correctly and you thought that was the standard deviation, and same thing for right here. So if you approach that as though it was standard deviation, you would have got 0.2174. So that explains that error. The other ones, I don't know exactly where the error was, but you can hopefully correct yourself from that. All right, so I wanted to jump into some review problems for this test, and I'm just going to run through. I have some specific problems picked out, but as far as this goes for today, if you have, if you want to pull up this presentation in Canvas, you can kind of look over these questions on your own because I'm not going to look at every one of them. And I have the answer key in Canvas as well. So if you want to rush through, or not, if you want to go through this, check all your work and then make sure that you're coming up with the right answers, then the answer key there, I can guarantee, is correct. All right, so that's the idea. And yeah, I'm going to pause real quick. Okay, so anyways, we are looking at random variables. We have a probability distribution, and the one thing I wanted to point out, this is unlike our normal probability distributions, but we have seen stuff like this before. It is a cumulative probability distribution, or probability distribution. So that means that all of these values represents the probability right here. This is going to be, you have a 0.8 probability of getting 9 or lower. So if you want the probability of just 9, then you'd have to do 0.8 minus 6, so that's going to be 0.2. So this probability on its own is 0.2. That's 0.2. This is 0.2, and so on. And the probability of 5 is 0. So if we see how that's added, we add 0.2 for each one. So now let's look at this. Khalid claims that the distribution of random variable y is skewed to the left with a mean equal to 8 interviews. This is the number of interviews conducted for job openings at a company. So we can see with 0.2, the probability distribution will be uniform. And no, so we need to find this one. So it's uniform. Okay, here we go. Now the question is the mean greater than 8 or is the mean equal to 8? So the mean, because this is uniform, the mean is going to be, this is going to be symmetric, and we can figure out that the mean is going to be right where our median is. They're going to be the same. And the median here is 8, so the mean will be equal to that. If this was an odd number, let's say we had like 11 right here, sorry. And we had another probability. So if this was different, then we might even want to plug this in as a probability distribution in our lists and figure out where the mean is. You could probably figure this one out without needing to use your calculator. But if you needed to plug this in to figure out what the mean is, that's a good thing to do. So anyways, at this point, the mean is equal to 8 interviews. All right, like I said, we have a number of problems, so I'm just going to skip through. And if any of these are ones you want me to slow down on to explain, then we can do that. So right here, we've got another archery problem. We really love archery with probability, don't we? We've got the probability that, I'm just going to skip to the final question. What's the probability that the number of times Luke will hit the inner ring of the target out of the 5 attempts is less than the mean of x? So I know one thing I'm going to need to find is the mean of x. And I can do that with a probability distribution. So, sorry, so if I create lists right here, I can do, let's see. Okay, we can do this a couple of different ways. I can actually plug this into list 1 and this into list 2, and I could run that. But I could do it a little simpler because keep in mind it says that there's a probability of 0.9 that Luke is going to hit the inner ring. And he has 5 shots. So we actually have a very simple way of doing this. If we want to figure out the mean of this, it's just going to be the number of trials times the probability of success, which is just going to be 5, times 0.9, which is 4.5. If you didn't think of that and you plugged it into lists and got that, did it that way, it'd take a little bit longer, but you'll still get 4.5. So what's the probability that Luke will hit the inner ring of the target out of the 5 attempts? Less than the mean. So that's any of these outcomes. And of course, maybe in my mind, the simplest thing to do is just take the complement. So this is a probability that he's over the mean. So 1 minus 0.59 essentially gives me 0.41. So there's my answer. Okay. A box contains 10 tags numbered 1 through 10 with a different number on each tag. A second box contains 8 tags 20 through 27. One is drawn from each box. And what is the expected value of the sum? We need to figure out the expected value for these 10 tags. Now, there's only one of each number, so it's actually pretty straightforward. I've got 10 numbers, so 1, 2, ... up to 10. Each one of them has a 1 in 10 probability of being picked. So it works out really nicely right here, if you're creating a table, that this is basically just going to be the average. I could do 1 plus 2 plus 3 plus 4 all the way up to 10 divided by 10, and it's going to end up being 5.5. Again, you could put these into your lists on a calculator and come up with this 5.5, But if you realize it's all the same probability, it's a uniform distribution, then it's just going to be the average of all your outcomes. Same thing with the next one. If you get the average of 20 through 27, and my shortcut that I'm doing is I'm just taking the 20 and the 27 and getting the average of those two, which is going to be 23.5. So everything else, I'm still going to average out 23.5. All right, so if that's not making sense, jump in. But bottom line, at this point, the expected value is going to be the sum of these two, which is going to be 23.5 and 25.5, or sorry, 23.5 and 5.5 added together, which is 29. So that's what we would expect to get on average if we combine one tag from each box. Okay. Good stuff right there. Again, let me know if, I keep saying jump in if you have any questions, but so I maybe should stop saying it. Was I going to do this one? I was going to, let's see. Should I skip this one? I have to see something real quick. I was going to skip this one and we'll come back to it if there's time. All right. So now we're looking at this problem. And what we've got is a computer card game, 5 points for every card in the correct position, minus 10 for each minute the game is played. Now what we've got is a random variable that represents the number of correct cards in position. And then we have another random variable y, which represents the number of minutes the game is played. So this on its own, we don't want to combine those. We first of all need to rescale, transform this data. So I want to not do x, I want to do 5 times x, and not y, but 10 times y, because we're going to convert these into points. So we have a common unit when we combine these together. So if I convert these into points, luckily by scaling this, all I have to do is multiply both these numbers. So the new numbers is going to be 5 times 9.5. Let me get out of this. So 5 times 9.5 is 47.5. 12.9 times 5 is going to be 64.5. When I rescale the others, that one's pretty easy. It's going to be 54 and 11. Okay, so at this point, we can combine these because we're going to take x, which is the positive points that we earn, minus y, which is the negative points. So I'm going to do x minus y. So the mean of x minus y is just going to be 47.5 minus 54, which is negative 6.5. We would expect to lose 6.5 points every time we played. And so it's going to be one of these two answers. Now we just need to figure out the standard deviation. Here's where we can combine the variances. So the standard deviation of x minus y is going to be the square root of 64.5 squared plus, it's always plus, even though we're subtracting the random variables, 11 squared. We could plug that in. At this point, you understand how I set it up. And the answer is 65.4. So we don't need to take time doing that. So there's your answer for that particular problem. I'm going to skip this one. I'm going to do this one, though. Transaction history at an electronic goods store indicates that 21% of customers purchase extended warranties. And suppose customers who buy eligible items are chosen at random until one is found who purchased the extended warranty. So hopefully your brain is already starting to think about what kind of probability are we looking at here. Let the random variable x represent the number of customers it takes to find one who purchased the extended warranty. So you never see it in here. They never actually use the word, but we're looking for the first person. So if it's the first person, that's telling us, okay, they either buy the warranty or they don't, so it's binary. Each person is going to be assumed to be independent. And in fact, it even says right there. We're looking for the first, and it's the same probability each time, which is 21%. So this is going to be a situation where we're using the geometric probability, geometric distribution. So which of the following is closest to the probability that x is greater than 3, that it's going to take more than 3 customers. So basically, we don't want the first, the second, or the third customer to buy the warranty, but anything 4 and beyond is great. All right, so all I need to do in this case is going to be my geometric CDF. This is cumulative probability. I've got a 0.21 probability of success, and I want to go all the way up until the third customer. So if I do that 0.21 and 3, there's a 50.7 probability that one of the first 3 customers will buy one. Now I don't want that, so the complement of that, so 1 minus that, is going to put me at about 0.493. So there it is. There's the answer. Moving forward, I wanted to skip this one as well. Yeah, that one's actually pretty straightforward. I was going to skip this one. I'm not going to go through it all, but basically the question is, under which of the following situations would x be a binomial random variable? So we're basically, for all of these right here, you're going to check bins. See which one has the bins. All right. So you can do that in your own time. You can double check your answers. Like I said, the answer key to all this is on the Canvas page. So if you're looking at this one, you can double check to make sure you got it right. This one in particular is a good one to run through. Is it? Yes, it is. We're going to find out among 9 volunteers who can determine the difference between bottled water and tap water. And each participant will taste the water from 2 different glasses, then identify which glass he or she thinks contains the tap water. Assuming that there is no difference and people can't taste the difference, what is the probability that at least 8 of the 9 participants will correctly identify the tap water? So we have 9 trials. This is going to be bins. So it's the same probability each time. Our probability here is, well, it doesn't tell us. So, but except it does say that there's no difference. People won't be able to tell. So at this point, what that means is there's a 50-50 chance they're going to get it right. So that's what that means in practice. The number of trials we have is 9. So at this point, we want to find the probability of getting 8 or 9 successes out of 9. So pretty straightforward at this point. It's going to be binomial CDF. And I want to figure out the probability that, since I have to go left to right, that anywhere from 0 to 7 people guess correctly. And whatever the complement of that is, in fact, I could write it like that. Whatever the complement of that is will be my answer. So it's going to be 9 trials, 0.5 probability for each one. I want to get up to 7 successes. And you can actually type it in your calculator that way. You can do the 1 minus, then pull up your binomial CDF, which is going to be 9 trials, 0.5, and 7. And I got, basically there's a 2% probability, but we want a little more. No, that's good enough precision. So there it is. So only a 2% chance that by random chance you're going to get 8 or more successes. Next problem. Okay, this is a fun one. We've got, but actually having done some other problems already, this one won't be too bad. 10% of all dynamite candies are orange, and 45% of all holiday mint candies are orange. 2 independent random samples, each of size 25, are selected, 1 from each type of candy. The total number of orange candies in the two samples is observed. What's the expected number of orange candies and the standard deviation? So let's talk about this. I need to find the mean. I don't want to use X here. I'm going to use D for dynamite mints. And I'm going to use, what's the other? Holiday. I'm going to use H for that. So the way that we can find the expected value, because it doesn't tell me the expected value, but what it does do is it tells me we're going to have a sample size of 25. So I'm going to have 25. And there's 10% of these. So times the probability is 0.1. So that's going to be a 2.5 expected value. Same thing here, except now it's a 45% for holiday mint. So I'm going to do 25 times 0.45, which is 11.25. Before I move on, I wanted to clarify something because I did just jump right into the calculations. But it is important to note that this is a situation where we're using the binomial setting. And that's why I can use these formulas where the mean of a random variable is just the number of trials times the probability of success. And that's because I can tell that I have this set number of trials right here. That's my in. So that's going to be my giveaway right from the beginning. Okay, this is binomial. Therefore, I can find the expected value of this binomial situation. So now that we've got it, the combined number of orange candies, maybe if I put all 50 candies together, it would be these two added together. That's going to be 13.75. It's the 2.5 plus 11.25. 13.75 means it's going to be one of these three. And here's something you can use just as well, I'm jumping ahead. Let's go ahead and find the standard deviation. And here is where we have this formula, which is the square root of n times p times 1 minus p. And so I will just plug those numbers in. It's going to be 25 times 0.1 times 0.9, which gives me a standard deviation here, 25. This is going to be 1.5. That's weird how that worked out. It's 1.5 exactly. This is going to be the square root, that's an h right here, of 25, because that's our sample size, times 0.45 times 0.55. And that's going to be 2.487. So here is one hint as you're looking at this. Because we are always combining and because we're always adding our variances, the combined uncertainty will always be greater than either of the individual uncertainties. So we can automatically rule out C, because notice that the standard deviation right here is 2.23, and there's no way your uncertainty ever goes down. It always increases. So we can know, that's just, it might not even be that helpful because you're going to have to do the calculation at this point anyway, but it's just good to know. So when I combine these, the standard deviation of D plus H is going to be the variances combined, 1.5 squared plus 2.487 squared, and that'll give me the final answer here. Which is 2.90. And because that should be a 9, sorry. Because of my rounding, I got 2.904, but obviously this is our correct answer. Okay. The hope is that as we go through this, you're not getting more confused, but getting less confused. I guess that's not always true. This is going to be a pretty good question as far as just understanding the binomial distribution, what it looks like. Remember that it's going to be roughly normal but it can be skewed. We have the large counts condition, and I just tend to write it LC for large counts. That determines if it's normal or not, but I can automatically start thinking about which one makes sense at all. Well, these two don't make any sense. This would be a good one for the geometric distribution, but we're not talking about a geometric distribution. So C, D, or E are the only possible answers, and we can figure out which one makes the most sense. If I know the sample size and the probability, then the mean of this is going to be where n times p is, and 20 times 0.25 is, I'll just write it in. So 20 divided by 4 basically is 5. I want to find one of these that is centered around 5. This one is centered at 10, so that's not it. That one's centered at 15, that's not it. So it must be this one. We can see that's centered right at 5. There's your answer. And I will say this is not technically enough failures and successes to be called approximately normal, but that's okay. They're not asking us to do that in this problem. A die used in a certain board game has 8 faces, of which 3 are red, 3 are yellow, and 2 are blue. Each face is equally likely to land face up when the die is tossed. In the game, a player tosses the die until blue lands face up, and the number of tosses before blue lands face up is counted. For example, a player who tosses the sequence shown in the following table has tossed the die 3 times before blue lands face up. All right, and that's just all set up for this question. What is the probability that a player will toss the die at least 2 times before blue lands face up? So there are different ways of approaching this, but one way that immediately comes to mind for me is that we're talking about when is the first blue going to show up. And the first blue, we want it to be at number 3 or later. So we basically want to figure out the geometric probability that it's your maybe on the first or second toss that you get a blue, and then get the complement of that, which means let's figure out our probability. So we don't need an n here. We're not talking about a set number of trials. We could toss this forever if we wanted to. So it's not Ben's, it's going to be Biff's. And we have the same probability each time, and the same probability here. So let's see, if we look at this die, how many? There are 8 faces, 2 are blue. So the probability is just 2 out of 8. So that's, we can use 0.25. That's just as easy to use. Doesn't want to write at the edge of the page. 0.25, there we go. Okay, so let's figure this out. We've got a geometric CDF, and we want to have a probability of 0.25 and go at least 2 times. So the first or the second trial, so we can figure that out, but we want the complement of that. So it's going to be 1 minus the geometric CDF. And I got 56.25%, 0.5625 when I did that. And there it is. That seems correct to me. You can let me know if you have any questions on stuff that we've been talking about, of course. All right, this is what I wanted to look at. It's a very simple question, but I will say that when I've asked questions like this in the past, it's something that students forget about a lot. And you have this. I forgot to show you something real quick. I told you I was going to show you the AP formula sheet, and I'm not sure that I ever did. So if I go back here, some of you have this and you've been referring to it. And especially moving forward, you're going to make this a daily reference. But if you haven't really started looking at this yet, then I encourage you to get it downloaded to your iPad. Even if you have access to a printer, get it printed off so you can just have it on paper next to you. So we've looked at this before and we've already covered all the stuff with descriptive statistics. Here's your chapter, your unit 5 probability. There's very little by way of formulas that they give you. But when we move down here into probability distributions, notice they give you the formula for binomial. They give you the formula for your binomial PDF. And it's a good idea if you're doing a PDF calculation to actually fill in the numbers. If this is an FRQ, you actually want to show this formula with numbers put into it, but you can still use the calculator to do the real calculations. Geometric down here. So notice that we have the mean and the standard deviation formulas given. And what this is asking for, let me go back to this and I'll probably go back and forth a little bit. Random variable W has a geometric distribution. So it's going to be geometric with a probability of 0.25. Approximately how far do the values of W vary on average from the mean? So
is it like a z-score?
This is actually your standard deviation.
Oh, okay.
Yeah. So good question. I'm glad you asked. So it's asking for the standard deviation, and all we need is the probability. Because when we look at the standard deviation for a geometric distribution, we've got that right there. So if I copy that formula over, this is, I'll project this again. So the standard deviation of this random variable is going to be square root of 1 minus p over p. So that's going to be square root of 0.75 over 0.25. And we can just figure that out real quick. It's 3.46. There's the answer. So this throws people off because they don't know what they're being asked to solve for. But if you understand that it's just asking you to find the standard deviation of a geometric distribution, then it's incredibly easy. Okay, we're getting close to the end, and hey, we're actually going at a pretty good clip, so I'm feeling good. And then watch it slows down. I'm going to skip this one, but this is another one where you're basically asked to check. Sorry, I skipped over it. Go back. You're being asked to check, in this case, since it's geometric, check all of these right here, see if BIFS is being met. Or in this case, most of them will work, but one of them should not be modeled with geometric. So which one is not meeting BIFS? And 4 of them will. So I'm not going to do that one, but I want you guys to practice with that and check your answer after you're done. I will skip this one. This is just another problem where it is using cumulative relative frequency. All right, so we already looked at that with one of the first questions. So the relative frequency for each one is right here. Notice we're just adding on to the next one. So it went from 0.910, add this 0.009, now we're at 0.919. So the cumulative relative frequency of getting this value or lower is constantly being shown. So anyways, I encourage you guys to try this problem and make sure you can get it right. But it's just a more complicated problem that's the same thing as what we already looked at. And this one looks really challenging. This is the last problem we're doing. Yes, it is. This is an FRQ we're going to run through. And I mean, I know what some of you might be thinking. You're looking at this and you're saying that is a lot of reading. And maybe you go into a question like this nervous about being able to even interpret what you're being asked to do. So hopefully you realize at the end it's not that bad. The last one's going to be the trickiest problem, which is usually the case. But we can do this. We can do this. So an important method for controlling the spread of bird flu is a specific strain, is to check a group of chickens. It's called the Elisa test. Now, we already ran into that before. And if the Elisa test reveals a high enough concentration of antibodies, the chicken is said to be positive and is classified as infected with the virus. Otherwise, if it's said to test negative and is classified as not infected, but it's not always accurate, and we'll learn about the errors that we get. One type of mistake, and we'll see the probabilities down below, but the false positive is when you get a positive result for a chicken that is not infected. False negative is when you get a negative result for an infected chicken. So that's important, and it does explain it in the prompt. One thing I'm going to say about FRQs is they do give you a lot of information, so I would read everything. And we've already seen sometimes I fail to read, so I'm trying to do better about that. So here's the process that they use to determine if the virus is present. They select 10 chickens randomly, perform the test on each of the 3 chickens, and if at least 3 of the 10 have positive Elisa test results, then you have this virus in the flock. Isn't that comforting to know that there could be 2 chickens that have the bird flu virus and they said it's not there? That's good to know, right? So now this veterinarian applies the procedure to a flock of 100,000 chickens. It's a good thing we're dealing with only 10 chickens because that would make our calculations, well, the calculator's doing it, so it wouldn't be that bad, but still. All right, let's see what's going on. We've got a false positive rate of 0.05. We've got a false negative rate of 0.10. And we're still just checking 10 chickens, so make sure that's still understood. Let's go ahead and start answering the question. If no chicken in the flock is infected with the H6N2 virus, what's the probability that the veterinarian will conclude that the H6N2 virus is not present in the flock? So we basically are trying to figure out if it's not there, what's the probability that's correctly decided? So you'd think it's 100%, maybe a lot of people would think it's 100% if there's no chicken, but we could get some false positives, right? So what's the probability of a false positive? It's 0.05. So we want to see what's the probability out of 10 chickens that we have 3 or more false positives. So I will do a binomial. Let me write it down here. Binomial CDF, because I want to see what's the probability that I get out of 10 chickens with a probability of just 0.05. What's the probability that 3 or more?
Mr. Davis?
Yeah.
Wouldn't we want to use the false negative?
No, that's a good question. The false negative is whenever a chicken does have the virus, but we get a negative as a result on the test.
Isn't that what we're trying to use? Because it says if no chicken in the flock is infected, what is the probability that
yeah, I thought it was
present in the flock?
like none of them test positive, then what's the...
You're right. I should have done things differently. Of course I should have done things differently. Thank you for catching that. What I want to use is the complement to this. I want to use 0.95. So I'm still using this 0.05, but I want to figure out what's the probability that I get. Actually, let me reset and let me still use this 0.05 and I'll explain why. So I want to make sure that I don't get more than 2 false positives. Does that make sense? So I've got 10 chickens. Each chicken, we're going to assume, has a 5% chance of getting a false positive. And I do not want to get more than 2 false positives. Because if I do, then they're going to conclude that this flock has the virus. But if it's 0, 1, or 2, we're good. So is that making enough sense, or do I need to explain further?
I
So-
thought the question was they all test negative, and it's a probability of how accurate that was.
It's not exactly asking that. The assumption is that none of the chickens have the virus. They haven't been tested yet, but we're going to go on the assumption that there are no chickens with this virus. On that assumption, what's the probability that it would show up as though the virus was there because of false positives?
Okay, thank you.
Yeah, that makes sense.
Okay, good. So, and you do raise a good point, because we don't really know that there's no virus in the herd. So this is kind of an assumption that we're making from the beginning. I say the herd of chickens. Let's go with that. All right, so let's go ahead and calculate this real quick. So if I do my binomial CDF of 10 trials and 0.05 is a probability and 2, then I've got 0.9885. So there's a 99% probability that we will correctly deduce that there's no virus in the flock. I do want to point something out before we move on. This is the calculation we need to do, but this does not suffice as an answer. So of course you're going to need a sentence that says there is a 98.85% probability that the veterinarian will correctly conclude that there is no H6N2 virus present in the flock. But beyond that, we need to clarify some things. You can't just throw this on your page and show that that's good for your work, because you will lose points. So it's important to show what these numbers mean. So if you just have off to the side, you say we have 10 trials, so n equals 10, and there's a probability of 0.05, and we want, if you made something to the effect x equals 2, and then kind of clarified, we want no more than 2 false positives. You will need to put some explanation for your calculation, because just calculator speak is not good enough. But calculator speak in addition to explanation is fine. So I probably won't do that out of laziness right here, and I'm being a bad example, but I wanted to point it out for the first one. And then when I do all these others, keep in mind, I'll kind of briefly talk about what you need to show. So I'm going to create room here. All right, now we get to the next one. If no chicken in the flock is infected with the H6N2 virus, what is the probability that the veterinarian will conclude that the H6N2 virus is present in the flock? And show how you find your answer. You guys can answer this. What's the probability that they will conclude that it's present?
Is it just the opposite of 0.9885?
Yeah, it's the complement. So if I can squeeze this in, it's just going to be 1 minus 0.9885, which is going to be 0.0115. Just over a 1% probability that's going to happen. So again, write your sentence, and you could write a sentence explaining to say, this probability is just the complement of my answer in part A. And if you show your 1 minus that and explain how you're doing it, then you're good. Okay, the next one. Now we're going to shift our assumption. If every chicken in the flock is infected with H6N2 virus, what is the probability that the veterinarian will conclude that the virus is present in the flock? So now, what is the probability of the Elisa test correctly diagnosing the virus is present for a chicken that has the virus?
So would you do binomial CDF with 10 trials at point 1 for the producing a false negative, and then would you still have would you do 8 instead of 2? Because if you have if you have 8 negative, you're fine.
I see where you're going, and actually, you raise an interesting point. We could think of all the different ways of calculating this, and we'll get equivalent answers. So we could do. So you're saying the binomial CDF. We have 10 trials. We want to find the probability of a lot of false negatives. So 0.1 is the probability of false negative. We want to get up to 7. So we could get a certain number of false negatives, but only up to 7. Because at that point, 1 minus that. So this right here represents the probability of getting anywhere from 0 to 7 false negatives, in which case they're still going to determine that there's virus in the flock. If we get 8 or more, then they're going to conclude that there's not. So this is one way of calculating it. Can anyone think of a different way of calculating it? Okay. I do want to give you guys some time to think. I'm not just going to show you what I'm thinking of. All right, I'm going to go ahead and jump in. Now, you get equivalent answers either way you do this. Here's option 1. I'm just going to put a circle around this. Option 2 is, what if we looked at it from the other way? Like, what's the probability that the test is we get a true positive instead of a false negative? Okay, so the probability of a true positive, when a chicken, so if a false negative is 0.1, then there is a 0.9 probability that this will be concluded correctly. And so here's what I'm going to do. Binomial CDF, 10 trials, 0.9 probability, and I want to see the probability that there's only 0, 1, or 2 chickens that test positive. And if you try both of these in your calculator, you get the same answer. And that number is very, very small. So that's going to be, basically there's a 0.9999996 probability. 6263. All right, and that's kind of a tough one to put into numbers, but you're almost guaranteed to conclude that the virus is present. And the reason this is so much higher as a percent than the other one is because the burden of proof is much higher. In order to conclude that there's no virus, you'd have to get 8 false negatives. In order to conclude that there is virus incorrectly, you only need 3 false positives. So the fact that you're doing 8 false negatives versus 3 false positives, that shows why there's such a difference in the probabilities. Okay, I'm going to pause right there and see if there are any questions. Okay, so again, just a reminder, calculator speak like this is not good enough. Make sure you clarify what your 10.1 and 7 stand for. And it's always good just to provide a little explanation. Why you chose those numbers, what your thought process is for selecting that calculation. If you do that, then you can write out your binomial CDF and you're good to go. I'm going to clear this screen for the last one. So hopefully, if we need to return to any of these, I can certainly do that. Here is the one that is probably going to be very tricky for you, if the other ones haven't been already. If 20% of the chickens in the flock are infected with this virus and the other 80% are not infected, and this is more realistic, right? You're going to have some split. What's the probability that the veterinarian will conclude that the virus is present? I keep wanting to say veteran whenever it's veterinarian. In fact, when I grew up and people said that they were vets, I used to think that they were veterinarians and not veterans. So maybe I'm probably not the only one who had that confusion growing up. All right, so let's look at this. We need to figure out the probability in a situation like this that we are going to get a positive result. Whether it's a true positive or a false positive, it doesn't matter. What's the probability we get a positive result? And this, we need to use a tree diagram. All right, so at the beginning, I'm going to try and squeeze this tree diagram in. There's a 20% chance that the chicken has the virus. So 0.2, I'm going to put Y for yes, they have the virus, 0.8 for no, they do not. Now, what we know is that when there is a chicken with the virus, there is a 90% chance they will get a correct positive diagnosis. There is a 10% chance they're going to get a false negative. All right. When a chicken does not have the virus, there is a 5% chance of getting a false positive. So 0.05, I'm squeezing this in, so I apologize if you're having a hard time seeing it. There's a 5% chance of a false positive and a 0.95 chance of getting a true negative. So what's the probability that I get a positive result? I don't care how I get it. What's the probability of getting a positive result? I can multiply this out. So 0.2 times 0.9 gives me a 0.18 probability of getting a positive from an infected chicken. And if I do 0.8 times 0.05, there is a 0.04 probability of getting a positive from a chicken that's not infected. And the other probabilities I don't care about as much, but it's going to be 0.02 and 0.76. So out of this scenario, if I combine these two together, there's a 0.22 probability that I will get, that a chicken will get a positive result, whether it's a true positive or a false positive. Okay, so is everyone good with this so far? Okay, and this is the challenging part of the problem because now it's pretty straightforward. If that's our probability of a positive at this point, now I can just use a binomial CDF. And we want to figure out the probability that it is concluded that there is, the virus is present, not president. I'm not talking at all today correctly. So let me see, I've got 10 trials. There's a 0.22 probability. And as far as this goes, let's see, how many successes are we looking for? What do you guys think? How many successes are we interested in for this particular problem? So remember, this is the probability that we get a positive result from our test. If I get 0 positive results, we decide there's no flu. If we get 1, if we get 2, we decide there's no flu in the flock. If we get 3, 4, or higher, any of those, 3 plus, we determine that there is flu. So what I want to do at this point is I want to figure out the probability that we don't find out that there's flu. So we get 0, 1, or 2. And let me erase this real quick. I want to get the complement of that. 1 minus the probability of concluding no virus. It gives us the probability that they will conclude there's virus. Okay, and when we do that, I will let you guys look at this, make sure you get the same thing. I got 0.3831. There's about a 40% chance that they will conclude that there's virus here. All right. So there's nothing for you guys to do tonight except to get ready for the test. And I say tonight, over the weekend, to get ready. So just come to class. Again, this is not tomorrow, Monday, ready for the questions. If you look over the stuff and you're still not getting it, come ready with that. We can hang out that class and just get you to a good spot. So in conclusion, if you want to look at this problem some more, if you want to see how to do that airline problem, because it came to me after the fact. Anyways, if you want any of that, stick around. Otherwise, you can have a wonderful weekend, and I will see you on Monday.
Mr. Davis, I have a quick question.